So I'm Dave Guerts. A couple things to know about me: when I'm nervous or excited, my skin goes blotchy red. So if that happens, that's normal. And then my beautiful wife and kids are here, so now I'm even more nervous. And then my nephew's here, is learning how to program. So he's pretty stoked on learning how to code. So first of all, everyone go to, if you have a phone or a computer, go to UtahJS.surelink.com. And there's just a little interactive thing where you can answer questions. So you can pull that up while we're getting going. Let's see here. So I came from the gaming. I did a lot of gaming when I was young, and I actually got my first job in gaming 21 years ago, doing QA at a company called Access Software. I did QA for a golf game there, and I just fell in love with programming. I would stay late and talk to the programmers, and it was just a blast. So that really launched me into programming and gaming. So I wanted to give a talk about some gaming concepts, because I know a lot of you guys are super into JavaScript, but not a lot of you maybe have gotten into games, and it's not that big of a hurdle. So I wanted to teach two concepps. So there's two common concepts in gaming called Ray Casting and Pathfinding. So we're going to go over those. So my name's Dave Guerts, like I was saying, and this is Chris Lemke. Some of you guys might know him. He's a React engineer at SureLink, and I'm one of the co-founders and the CTO of SureLink. So we do accounting software. And yeah, we're actually hiring if anybody's interested. So like I was saying earlier, if you go to that URL, there's going to be an interactive little portion. And then we brought prizes. So there's Thanos' glove from the Avengers, the little lamp for your desk. And then apparently the world's smallest arcade machine, which I doubt. I think that's false advertising. And then we have some USB keys, where when you plug them into a computer, they randomly move the mouse around and type stuff. So you can use those for fun. So if you go to your, hold on, out of there, over to here. So if we're lucky, you guys are going to see a quiz on your phones. After it loads, refresh. Oh, if you've already loaded the one before this, you might need to clear your cache. So anyways, I'll give you guys like 20 seconds. If you got lucky and it loaded. Oh, cool. There's some people up there. Yeah. So, all right. I'll give you 20 seconds to answer this one. Kind of a funny little question. So, yeah, like I was saying, we're going to learn about pathfinding and ray tracing. So pathfinding in a game is you want an NPC or your character or anything to be able to move around a map. So to be able to get from point A to point B. So some famous games that did that were like Zelda, the top-down 2D games. And then with ray casting and ray tracing, so there's two uses for it. The first use was in Wolfenstein 3D. And they used ray casting because 3D engines didn't really exist back then. So it was 2D shapes, and you use ray casting to decide if something is behind a wall or not. So that's how they would create the tunnels and the hallways and stuff like that. And then you can also use ray tracing to shoot a bullet or to look out of a camera and see if you see something. And you can scan around. And so there's a lot of use cases for that. So first, we're going to talk about pathfinding. So pathfinding, it really came about back in the 50s and 60s, and it was all driven by money, obviously. It was to find the shortest route for delivery was some of the first use cases. And then it was heavily used in robotics. Some of the first robots use pathfinding to try and get around rooms. And the problem back then was all the algorithms to do pathfinding were really expensive computationally. So we're gonna get into that. So I don't even know how to pronounce this. Dijkstra's algorithm was the first one that came out. Oh, there we go, Dijkstra. And it's pretty similar to the one we're going to learn about, which is A*. But this algorithm, as it was going along, if the environment changed or it was too complex, it would get stuck. One of the most famous use cases was a programmer named Chris Crawford. He was trying to make a game where it's these tanks that shoot each other. I don't know if it was for like the Commodore 64 or something. But they would go into a corner and just get stuck and spin around based on the shape of the map. And he essentially gave up on it and wrote some stuff about it, which spurred people into creating A*. So A* improved upon the last one, and the first paper that came out on it was in 1968. So there's two dudes, Niels Nielsen and Peter Hart. So they were trying to take this robot thing and move it around the room and get around obstacles, and it just wasn't performant enough, and it would get stuck. And they found a way to have the algorithm kind of keep on path as it was going, I guess is one way to put it. So here's the algorithm right here. So it's the f equals g plus h, and the n represents that it's recursive, and n is the next node in your search list. So using this algorithm, the older robots and things could actually efficiently move around a room. And so that's kind of where it was born. I'm going to pop some more quiz questions over there. Let's see if the leaderboard's updating. No? All right, quiz 2. So there's another quiz question up there for you. So I'll give you guys like 20 more seconds. So anyways, that's a little bit of the history. Obviously, gaming picked up on these algorithms real quick. So that's where it gets interesting for me. So I used A* I worked at a place called Wildworks, Smart Bomb Interactive, and we made a little bunny game. And the bunnies needed to be able to fly around these tunnels. And that was the first time I ever played with A*. And it was really magical to me, and it was one of like the first times where I implemented like a magic algorithm, kind of a black box that, and it just made sense to me why it was working. And I don't know, I thought it was really cool. So anyways, we're gonna now apply A* to gaming. So there's a couple things you need to be able to do this. So you need a level, right? A room or a map. And we're only going to cover 2-dimensional and top-down. But whatever you're working with, whether it's 3D or anything, you've got to break it up into a grid. So you need a grid, obviously. And then you need a starting point and an ending point. Pretty obvious. And then, so the grid is your search area. So after you've broken your map up into a grid, all of the nodes, I'm going to call them nodes, but whatever, the blocks, you need different types. So you need a walkable type. I mean, you need whatever your game needs, but walkable, not walkable. And then you can have walkable ones that are slow or deal damage. And we'll see how all that comes into play. So then A* has 2 lists that it uses throughout the algorithm. So there's an open list and a closed list. So the open list is any nodes in the map that you are able to walk through, or that you're going to consider walking through. And the closed list, as you go, when you find non-walkable nodes, you're going to add that to the closed list, and occasionally it will pop other ones that it's not interested anymore into the closed list. So so now that we have our search area, we have our nodes, we have walkable, not walkable, slowly walkable, our to list, open list, closed list. Now we have the magic algorithm, right? So it's F equals G plus H. And we'll go over what those are. So to calculate G, it's the total sum of the F scores to get to the node you're on. And we're going to go into all this in a lot more detail. Let's see. Is there another quiz question? Oh, we're already on 3. All right, we'll go to 4. Yeah, there you go. I'll just keep popping them in. All right. So to calculate G, it's essentially how far it took to get here. And by far, I mean movement points, and we'll see what those are. So G is essentially how much energy it took to get where we're at. And then H, and H is the new, it's the part that makes A* magical. And compared to the older algorithms, what H does is when it is considering which nodes to walk into next, it tries to find out how far away it is from the destination, which is really simple, but none of the older algorithms had this, and we'll see how it comes into play later. So H is one. You take the block you're at, like the pink one. Let's say we're there. We're considering the pink block. It's just the number of movements times 10 to get to the destination, which is the yellow. So here, it's 1 to the left, 2 to the left, 3 to the left, up 1, up 2. So 5 movements times 10. So the H score is 50.
Does that ignore whether this path is walkable or not?
It does. So they call it a heuristic, I guess is why it's H, in which it means it's a guess. So if it was actually going to reroute or take into consideration not walkable nodes, it would be, they've tried that and it just takes too much. It's not optimized. So somebody came up with the idea to just calculate how far away we are, not even determining like the terrain, and it's just way more efficient. It's really simple, but yeah, it works, and we'll see it. So we're gonna go into one example now. So we have the search area, we have our list, we have our algorithm. So now we have our hero. He's on a square, and he has his destination, which is the yellow one. So now we have to do a recursive loop over the algorithm and all of the squares. And I'm sure everyone here, most people know what a recursive loop is. It's when a function calls itself, and it iterates over and over until it's done processing. So here's our little starting point. So we're going to call this node the hero's on N1. So the way that you start out is you are on your node, and you get all of the neighbors. So you get the top left, the top right, left, right, right. So you get all of the nodes, and then so G is movement, and you apply a G score to all of the neighbors. So whenever you're doing a horizontal or vertical movement, it counts as 10 points, and you can weight these however you want based on your type of game. And then a diagonal move is 14, just because it takes longer to walk to the center of a diagonal node. And another thing that you're going to add to these scores is, let's say one of the nodes had sand in it and it was slowly walkable, that 10 would turn into a 20. Or let's say it was slowly walkable and had damage, like it was lava, that would be like a 30 or a 40. So your character would still consider going through it, but only if it's like last route to get to the destination. So that's how you assign the G score. It's 10 points for vertical and horizontal, and then 14 for diagonal. So then you take all of those nodes and you get their H score. And if you remember, the h-score is just how far away they are from the destination times 10. So like this top left one, it's 1, 2, and it goes through the non-walkable block. And then this one is 1, 2, 3, blah, blah, blah. So you get that, right? So now you create the f-score for each of them. So that's our magic algorithm, right? F equals g plus h. So all these nodes get their f-scores. Now, so we have all our f-scores. So now you take the lowest f-score, and that's the node that you're going to move to. And the character isn't moving there. You're just popping it into the open list and saying, I probably want to go there. And you can tell right now from this image that that's probably the wrong way. Oh, and there are no diagonal moves through blocks that are touching or across the corner with the block. So you can diagonal move there, but it couldn't diagonal move there and then there. So you can already tell it's probably going the wrong way. But that's the way the algorithm's taking it. So now this one, we're there. Now we get all of our neighbors again that we can walk to. We can't walk to this one because it's across the block. So now we need to determine, are we going to go to 10 or 11? So it's 10 points to go up, right? So now we take our f-score, because it's cumulative, and we plus 10 to it. So g is always the cumulative f plus the movement points. So the g is 44 there. Now we get the h of it, which is 3. 1, 2, 3, 30. So then the f is going to be 74. And now we do the same thing to figure out 11. So it has a g of 48 because it's a diagonal movement, so 34 plus 14. And then the h is 4, so 4 times 10 is 40. So now we have all of our neighbors from where we are, and all of these purples are in the open list still, so we're still considering all of them. So now that you're in N2, now you take the lowest f of all your neighbors. So 74, the algorithm figured out, I shouldn't have gone up. And it's not going to go to 88, so now it goes back down to 40. So A star made one bad decision, and it figured it out, and it figured out to go back. And that's where the heuristic came from. The older algorithms, after they got up here, would have kept going and gone around. So let's see here. So now we're back. Now we're down into N5, and the f is the cumulative f. So it was 34 plus 110 down, so that's 40. And now we're going to get all of our neighbors here. So to the left on N12, it has a g-score of 50 because of 40 plus 10, right? And then the h is 20, so now we have an f of 70. So you're starting to understand kind of how it works, right? It's pretty simple when you're looking at it, and it's actually pretty magical. I actually screwed up on the slides right here. This should have, this G should not have been 104. It should have gone at a diagonal down there, but let's just pretend I didn't. And so now the F is going to go through the bottom, and the G is 104 if you add it all up. The H is 30, F of 134. So like I was saying, that was a little mistake, but it still makes sense in the end. So now that, oh, wow, where'd I go? Ah. Oh, there we go. OK, so now you look at all your neighbors again, right? We have 70, 134, and 54. So we're going over to 70, but it should have added on the 54, so it wouldn't have gone there. Like I was saying, I screwed that up. All right, so now we look at all of our neighbors again. So we get N14, N15. You add the cumulative F and the left movement of 1. So now we have a G of 120, the H of 10, 130. Now it's going to check out 115, which is obviously going to get a larger score. It goes down at a left diagonal, which is plus 14, 2 movements of 20. And now we look at all our neighbors. Obviously, we're going to go to the 130, and we made it. So I don't know if anybody has any questions on any of that. Chris is going to dive into the code and how you implement it. Does anybody have any questions on the algorithm or anything like that? Nobody? Cool. Let's see here. What quiz question are we on? 4? Oh, we already did that one. Quiz 5. Ooh, I don't know if I told you guys the answer to this, did I?
Yeah.
Oh, okay. Yeah, sorry for the bad CSS. We have jobs and we cranked this out in the last like 48 hours. But it was a lot of fun. All right, what was that one? 5? We'll do one more. Here's one you guys should all know, right? All right, so now Christopher is going to jump on in. Oh, sorry. You get 10 more seconds for the quiz. All right, so now over to Chris. So you guys, yeah, Chris will go over it, but you should see this on your phones now as well.
All right, guys. So like Dave said, my name is Chris Lemke. I'm a React engineer with Suralink, bootcamp trained, JavaScript developer, and I'm coming up on 2 years just being familiar with JavaScript and playing around with it. I've been using React basically for as long as I've known JavaScript, so a lot of what I do, if it's web-based now, I try to see if it will fit into if it will make sense, or if there are benefits fitting it into the paradigm of React, right? Quick show of hands, React developers? Almost everybody. And quick show of hands, you've worked with Canvas before, HTML Canvas. Okay, so that's maybe 20% of you. So if you have worked with Canvas before, or if you've done any game development before, you know that the object-oriented approach is generally considered best practice. And lucky for us, React's underlying architecture is class-based, and you can essentially leverage it in an object-oriented way. So then the challenge was, is there a way to create a custom render loop using Canvas so that we could render a custom game experience, but then deliver it through React as sort of the application interface. And I'm actually going to switch over to code editor in a little bit, and we'll actually just walk through. It's a pretty simple implementation, and we'll just walk through it a little bit. Before we do, so we have, and you guys have maybe been playing with this already if this has shown up on your screen. So this is a basic 12 by 16 grid. We have our character in the upper left here, and our character is programmed to, once we click and set a destination, he's going to walk the A-star algorithm. So whereas normally what would happen is the algorithm would run invisibly, and then the best path would then be traversed by the character. In this case, it's set up so that our character is actually going to walk the algorithm. So you're going to see him maybe not always move perfectly linearly, but sometimes move into areas that he's exploring or that the algorithm is checking out. So let's see an example of that. And you'll see as he goes, the nodes that are in purple are nodes that have been left in the open list and never explored. The yellow nodes are obviously the path. And then what we're seeing is the cumulative score. So you can kind of see logically how as he moves through the environment and as our algorithm assesses the neighbors, he's assigning scores and he's following the path of least expense, essentially. One thing to note, we turned off diagonal. So he's only calculating the north, south, east, and west neighbors, as you can see. And he is not making any diagonal movements. And that's just to keep it a little bit more simple in the implementation and visually. Any questions before we switch over to code? All right. OK. So here's our, and so you guys know, in the UtahJS, in the Meetup Slack channel, we'll throw all these resources in after the talk, if you guys want to clone the repository and play around with it. So here's our interface. Any and all React developers will recognize this. And all we're doing, as you can see, is we're rendering the game canvas. The game canvas is the component that actually has our render loop, And this component, the game class component, the React component, is actually sharing context with our Canvas instance, which we'll see down here. Oh no, can I scroll with my fingers on here? Sorry, guys. Okay, so let's just look at this really quickly. We're importing some sprite sheets up here, just simple PNGs that we're going to use. Canvas is going to use them to draw our node tiles and our characters. A great thing about the React, underlying React architecture and algorithm is that we can utilize their lifecycle methods, which is actually quite nifty in this use case. So as you can see, we're just setting up a mode. Because this is a demo project, we have a Pathfind mode and a Ray trace mode. Oh, thanks, boss. This is the smallest mouse I've ever seen. OK. And some configuration. OK, so let's talk about initializing the actual canvas or setting up the actual canvas. So this is a method that we're using. And here's the other thing. So if you're creating a canvas renderer, there's going to be a base class because you're going to want that. You're going to want to be able to explicitly use the context. You're going to want to bind variables and methods to it. And it's the same with React. So again, we're just sharing context between the two. So our canvas methods are React class methods as well. The only thing to note that's different or unusual compared to like a typical React component is the only thing that React is rendering is the canvas element. Once the canvas element is painted to the DOM, we're never firing the React render function again. Through the canvas element, we start our own render loop, and then with canvas, we paint everything to the screen and handle all of the user input and all of the events and all of that. So first off, we're just grabbing the canvas ref and binding it to the class. We're getting the context so that we can actually draw to the canvas element. And then here we go. So we have a method here to basically paint our grid, right? I said it's a 12 by 16 grid. So what I've done is just created a method that takes in the number of rows and columns and then the total width and total height. The method itself will basically instantiate canvas objects based on dividing the total width by the number of columns and the total height by the number of rows. And then it's going to paint those onto the screen as we've seen. So each one of these nodes is a separate class instance, right? And actually, let's take a look at that really quick. Also, is this big enough for everybody? Yeah, Ken hooked it up. Yeah, OK. OK, so here we go. So the grid box is our, obviously, the node, right? The grid node. And again, like if you've done OOP before, if you've done Canvas before, this is probably going to look pretty familiar. We're using a constructor function, and we're going to pass in a bunch of configuration, right? So we can have one grid box object that could be a walkable tile, obstacle, a damage-dealing tile, a slow walking tile. And then it has all the methods it needs to talk to the other objects within the game environment. This is common object-oriented principles. So what our init grid function is doing is just initializing, in this case, 192 of them, assigning randomly whether they're going to be walkable, whether they're going to be an obstacle, whether they're going to deal damage, or whether they're going to be slow. And then it paints them to the screen. So we have hot reloading enabled in our example. It won't work in your guys's. Your guys are loading a static build. But that way we can change things and explain things a little bit. And actually, I'm going to jump over so that we can see without any poor CSS blockages. OK. So that's that. And then our hero. So again, coming back to our custom classes. And any methods that are relevant in walking through the algorithm, they'll get elucidated as we go. Don't worry about all that nonsense. Here's our character, very much the same thing. It's just a constructor that has properties that basically Canvas is going to read these properties and use them to determine what to draw to the screen or how to draw this object on the screen. And we'll get into that as well. So, OK, so we've rendered our Canvas element to the DOM. We've bound that Canvas context to our React component. We've initiated the level grid. We've initiated our hero. We have to add a few event listeners here. In this case, it's just a click listener. So we know that when the user clicks on a node, we want to set that node as the next destination for the hero, right? And then the hero can start pathfinding his way there. We're going to ignore this for now. Oh, yeah, and then this is just a little pause listener. We can ignore that as well. OK, so once we have all of our game objects instantiated, all of our event listeners in place, then we're actually going to kick the render loop into motion. So this is the render loop method. And we're using the built-in request animation frame. And that's just to make sure that everything runs smoothly. We're basically being nice and saying, hey, browser, can you grab this and paint this next time you have some free computing power, right? And it's super nifty. And it's going to pass in a frame timestamp, or a frame ID, rather, into this method. And it's going to get called recursively. And then we are, as you can see, we're binding the frame ID. So each time, it's going to return this frame ID. And we're going to bind it to our class so that if we need to cancel the recursive loop, we can with cancel animation frame. And these are built-in methods. So our render loop, if we look at what it's doing, first of all, it's invoking this draw render method. So let's look at that. And again, if you've used Canvas, you're familiar with this. So what our draw render method does is, first of all, it just clears the entire canvas. You don't see it happening because this is happening so many times per second. But it's going to remove everything from the canvas and start from scratch. So we're going to draw the grid again, based on new information. So let's say you clicked on a grid tile. So now we want that grid tile to be blue. So the next time the render loop goes through, we clear the canvas and then start redrawing each grid object. It's going to have the grid object is going to say is destination, and we can read that and we can paint accordingly. So it's just our own render loop. And every time it loops, we redraw the grid based on whatever info is necessary. And then we have this draw box function or method that takes in a type. So we can pass in a game object and a type, and this is just all preference, right? And then based on the type, we're going to grab values off of that object and use them to draw to the canvas. So that's the basics. I mean, that's the basic principle of getting a canvas render loop going through a React component. Certainly, there's any number of ways to skin a cat in programming, as we all know. So let's talk a little bit about the actual pathfinding algorithm. So if we look in our click listener here, so we're saying on click, if we're not busy finding a path right now, so if our character isn't busy currently running the pathfinding algorithm and moving, and if we've clicked on a tile that isn't the tile our hero's on, then we're going to set that tile as the destination, and then we're going to invoke this find path method. And this find path method is the beginning of the A* recursive algorithm running. So let's take a look at that. So this pathfinding script, again, a class just to stay with the OOP style, and so that from within our pathfinding class, we can access its own context, but then we're also passing in the context of our base class, our game-based class, so that we can read and write to that if we need to. So we're going to invoke the find path algorithm. The first thing we're going to do is make sure all the variables that we're using are initiated to the right values that we need. We're going to push our current position. So this is going back to the mechanics of the algorithm or the steps of the algorithm. So the open list is lists of nodes that we're open to the algorithm going to, reading the neighbors. So basically, like the algorithm hasn't said, no, this is not an option yet, right? So to get the algorithm going, we need at least one open node to read the neighbors of and to start the recursion. So what we're going to do is push our current position in. So we're saying, all right, we'll start here. We'll read all the neighbors here. And then we'll move on from there. And then we're invoking this iterate path method, which is, in fact, the recursive method that's going to, that is the algorithm. It's the core of the algorithm. So the first thing that we're going to do, we're going to go through that open list. And we're going to say, so this is just a catch, right? So each time the algorithm runs, we want to grab the, basically, first.
Oh, the lowest.
It'll be, yeah, OK. So the first time, it's just going to grab the only node that's in there, in the open list. And then moving forward, it's going to grab the lowest F score from the open list, set that as the next, and then move forward. So let me make a little more room here. OK. So if the next nearest, so if the node that we grabbed out of the open list is our destination, that's it. We end this is our stop case, and the recursion stops. We return out, and that's it. The algorithm's done running. Otherwise, we're going to see if this. Oh, sorry. We're gonna grab this node out of the open list. We're going to push it. Sorry, right here. We're going to grab the node out of the open list. We're going to push it into the closed list because we've already run all the neighbors. We've already checked it out. And then we're going to add it to the path object, which the path object is basically keeping the optimal path, right, as we go. So if our character was not following the actual algorithm but was running the algorithm and then taking the optimal path, that is the path it would take. And then, I mean, this is all like, it's basically just math, right? Recursive math, running the neighbors. For each neighbor, we're going to go through. We're going to calculate its G-score, its H-score, and then we're going to calculate the F-score. We're going to assign it to that neighbor. And so long as we haven't hit the destination path, the function will call itself again. It's going to choose the lowest score of the neighbors that it just assigned values to, move on to that one, and rerun. And so that's the magic. Much like Dave, and if you have like written recursive algorithms that function, it's pretty magical. It's very hard to visualize what must be happening in runtime with this function feeding, like invoking itself in this loop of computation. But it's pretty cool. And then we have our basic methods for calculating each score type. One thing we did add, so some of our, as I mentioned, some of our nodes are slow walkable, and some of them do deal damage. So we're raising the stakes on those. So we're basically telling the algorithm, like, think twice before, like, these are going to cost you, right? So try to find a more efficient path. And that's it. So let's where are we? OK, I'm going to go in here. So one thing we're doing right now for the example, for the purpose of example, is we're allowing a 300 millisecond pause between each iteration of the algorithm. And that's why he's moving very slowly and gradually, right? Bup, 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 bup. If we were to, so let me turn this off so our character won't move. So if we're to run the algorithm without a pause, you can see that it's essentially instantaneous, right? And so this is what's happening under the hood when you have NPCs or when you're playing a click-and-go game. And this is JavaScript. And not only is it JavaScript, but within the algorithm, as you can see, this is something that I have a little bit of shame about. But I was I was thinking C# when I wrote this. We're using these like recursive methods, like .find is in here a bunch of times. So this is not optimized. If we were to use objects instead of arrays, and we were to use associative lookup, let alone writing it in some language like C++ or something like that. This would happen almost instantaneously. Or you could do it on a much more complex level, and it would still be efficient. But because we're using JavaScript, it's not quite instantaneous. Do you guys have any questions? Or is there anything that I didn't cover? Yeah, sure.
So like for the slow motion, the painful spots, you add like a penalty to the algorithm. How do you know how much of a penalty to add for each of those?
It's like Dave said, it's kind of up to the game. Like as you saw, the A* has the 10-14 principle with horizontal and vertical versus diagonal movements. But beyond that, it's up to you. Like if it's lava, maybe it's more damaging than if it's toxic waste versus if it's a spike pit. So basing it on, let's look at the values, right? So we're saying 10 points to move north or south, 20 points to move diagonally, and then additionally 20 points to go through a slow point, or 40 is pretty high stakes. So you just have to think about how the algorithm is going to accumulate the F score, and you want to make sure that you're adding enough when the tile is, for example, damage dealing. You're adding enough that the algorithm is for sure going to try to find a different way, right? It's not going to say, like, I'll just run through it. I'll just eat the damage, right? Because going 2 tiles in the other direction would be equivalent. You want it to be enough so that it may possibly choose an alternate path. And I would say it's just tuning your game so that it feels right and so that the behavior is right.
Yeah, I'm kind of curious how you calculate the H factor, because it's proximity to the destination. Is that correct?
Correct.
And so how do you do that? Because I would think that you have to do like a square root, and that would be an expensive operation, right? You have to figure out how many tiles to the left and how many tiles up, and then you have to, it's like a squared plus b squared equals c squared, but you're solving for c. So you're doing a square root, but square root is often expensive.
Yeah, the interesting thing about A* is it's really simple, and all you do is count how many nodes away from the destination you are and times it by 10.
Exactly. So in the x and y dimension, like in each dimension, we're doing math absolute. So let's say you're here and you need to move in a technically negative x direction. With absolute, it's going to be a positive value no matter what. So in the x dimension, if we are 5 nodes away from the destination, that's all we need, and then we multiply that by 10, and then it's the same in the y. So the actual calculation is very simple. We're just applying absolute to a subtraction. The current location, the algorithm's current location, subtracted in one dimension, subtracted by our destination in that dimension, and then doing the same in the other dimension, and then we multiply that by 10.
That's a really interesting point, though. So you started thinking through it to use more complex math to be more accurate.
Yeah.
That's the magic of A*, is whenever whoever they are tried to come up with more complex solutions, it was too computationally slow. And when you would put it against A*, A* would win almost every single time when you take in speed and accuracy. Nowadays, it's not as big of a deal because of the processors.
Right. Yeah, square root isn't a big deal.
Right. But that's the magic of it. They would throw it up against way complex math, and A* would almost always win because of the CPU limitations.
Yeah, but here you're throwing out just a little bit of accuracy.
Yeah.
But in the end, you win because it's done iteratively.
Right. And it's adequate.
So there was a bunch of people who throwing all these crazy math algorithms together. Somebody came up with the idea just to count the nodes, and it ended up being more accurate and faster.
Thanks. Yeah.
So, at the beginning you talked about how the React component balance renders your canvas once, right? And you
Yeah.
said you set up your render loop.
Correct.
Is there any benefit to using React here? Because it seems like, if you have the canvas to want to work, you just use JavaScript too.
Yeah, so if all you want to do is render the game, no. You're adding like a huge dependency. You're adding this complex underlying algorithm that you don't need, the React reconciler. So no, like if all you want to do is just render a canvas, it's more efficient to just do a script and put it in an HTML file. But maybe you want to build a e-signature component for your production app with Canvas or something like that. So, like you shouldn't do game development in JavaScript, probably. But it's like we're combining our, you know what I mean?
We can do it in JavaScript.
He's like, let's do a talk on game development. I was like, yeah, I'll jam it in a React component. Perfect. But there are use cases where you want to serve up Canvas from within a React application.
Yeah, there's a lot of use cases, non-gaming wise.
Totally. But great question, because you're absolutely
You gave away
right.
our secret. We're working on e-signature.
Not open source. Any other questions? Okay, I did want to mention one other really quick thing for such a use case, or if you ever are using a custom render loop inside a React component. Ironically, should component update is your best friend, like the most feared and hated lifecycle method, is great because you just return false. You set it up to return false no matter what, so you're never re-rendering. And then any new props that are coming in, you just update your canvas whatever, whether it's the base class or whether it's an object or something like that, and on the next render loop, that'll be reflected in the repaint. So it'd be very easy to add, for example, a menu beside this in a higher up component that was then passing configuration data down in the canvas could be looping in real time using that all feared lifecycle method. Any other questions on pathfinding? All right. So Dave's going to talk about ray tracing.
Is there going to be some kind of permanent place for this? Because I want to play with it.
Yeah.
We
have a GitHub. We'll get.
Yeah, it's hosted right now on GitHub pages. So I'll put that link in there.
Cool.
All right, let's see if we have some more quizzes.
Dave also forgot to mention this hover.
Oh, yeah.
It's just magic. It's just a levitating platform, basically. Could win it.
Let's see here. So back to our talk. Code demonstration, quiz. All right, so this is going to go pretty quick.
Yeah.
It's a pretty simple concept with how we're using it. So I don't know if you remember earlier, there's a lot of really complex use cases for ray casting, especially back in the day when they wanted to emulate 3D without actually having polygons and things like that. So ray casting is how they draw these 3D worlds in 2D engines, and it relies on a method called ray tracing, which we're going to go over. And ray tracing, you shoot a line out, and it's going to tell you what it hits. Pretty simple. And you could use that for a lot of things. Like in a game where there's a hook, you could ray trace to where they shot the hook and then do coding to have them swing on it. It could come out of a shotgun. Out of the portal robots, you could ray trace and then increment the angle like a degree and scan and find enemies, things like that. There's a lot of really fun use cases. So ray tracing, you could use it for an enemy to scan and hit a wall, and then it could scan up till it finds the end of the wall, and then scan over till it finds the end of the wall over here. And then you could combine it with pathfinding to find which way around is quicker. And then you could do a lot of things, like if it saw a hero, it could call functions on other NPCs who then work together to kill it, things like that. So the point of this is you want to do ray tracing because it's efficient. You could do simple collision detection, but it's not very optimized for being able to scan a whole map. Like ray tracing can go forever, and it's going to be the same efficient. And I'll show you how. So it has two phases, so a broad phase and a narrow phase. So the broad phase is when you shoot the ray out. We try and take the map, and we use the initial ray to eliminate as many things as possible. So we use a grid system, and here, let's show an example. So we're in a grid, same thing as the pathfinding. So here's our little hero. Here's some green walls and things like that. So let's say the hero shot a gun or was trying to look around to see where to go. So it shoots the ray out, and it goes forever until it hits the edge of the map. And this is the broad phase. So what we can do with this information is, now that you have your ray, you can do collision detection along the ray, and it doesn't have to be perfect, right? You don't have to do collision detection every pixel or two. Like you can, and you would tune this in your game like anything else to make it work. But that's only 1, 2, 3. That's like 10 collision checks. Whereas, let's say you shot the gun and we wanted to collision check everything in the map, that would be hundreds and hundreds. This is 10 collision checks, and we're going to know right away things that we could possibly hit. So what you do is when it goes through the grid, you collision detect it. You do collision detection every, like I was saying, like 10 pixel distance or something. And then you add all the nodes that it collides with into a list. Now, all you have to do is simple bounding box collision detection. If one of the yellow boxes collides with one of the walls, then you know you can do really fine collision detection on this little area on the ray. So that's pretty much it. And we kind of ran out of time to show an example on this. But there's a lot of, I'll actually put some links when we provide all the materials. But this one is really fun when you want to start making your games really interactive. So like I was saying, it's the broad phase where you shoot a ray or a line out of a camera, out of a gun, out of anything, across the grid. Then you do collision checks. You base this on how accurate you want it to be, mixed with how efficient you want it to be. And then you know all the boxes in your grid that they collide with. Now we can ignore everything else. Then we go into all the yellow boxes. Is it colliding with a wall or an enemy or a hero? Then we go into that little space and do really fine collision detection. And that's how that works. Let's see here. I think we got a couple more quizzes so you can get some points. But yeah, does anybody have any questions on that? On the ray tracing stuff? Anybody? It's pretty simple.
Also, yeah,
concept.
would anybody want to see some embarrassing, like, partway there?
Oh no.
Because we got ray tracing started, but
You want to show that?
I mean, if people want to see a partial implementation.
I think you better do prizes.
You want to do prizes?
Yeah.
All right.
Ooh, that's exciting.
How do we see the leaderboard?
I didn't program this. Who coded this?
I don't know. Oh, we got to go to the slide one. That's what it was.
And I'll just mention that there are like for Canvas, there are libraries that export. There are libraries that do ray tracing, that do pathfinding. Some pretty comprehensive JavaScript libraries that you can find to do all this stuff without having to write your own logic.
So I just want to say real quick, so SureLink is hiring. And if anybody's interested in gaming, I know a lot of people at WildWorks. They're down south. They're by IKEA. So if you live down south and you love JavaScript, or you want to get into gaming, tools, all sorts of stuff. Like they don't just do math, right? There's like every role you could think of in a software company to a gaming company. So if anybody's interested in that, I can get you in there and get an interview. They do Node.js on servers. They do WebGL. They do a lot of JavaScript. But then also my company, downtown Salt Lake City, is hiring. We do a React accounting software app. We're hiring junior web people, so right out of boot camp, mid to senior. And then we're looking for senior server applications and then Linux infra and DevOps. And I actually know the winner, I think. Is that Brian Barrow? Yeah, I've heard of you before.
All right.
So come pick your prize.
Come on up, Brian. Or what would you like, sir?
And then we got James 007.
Do you have the flash drives?
Yeah.
What's this? It's like a hovering platform.
It's like a puzzle or something.
Yeah.
Oh, you got to go Thanos.
It has real infinity stones.
Just don't snap.
You're James? Yeah. Cool. Congrats.
And then Colton Hibbert and D Money Baller.
You have to show yourself, whoever that is.
And Bob. Do we have a Bob? Oh, wow. We had a lot of 700s. All right, come on up.
Yeah.
Some of you guys got lucky on the sorting algorithm here. We had a lot of ties.
Enjoy, sir.
We have 3 left.
3 left, yep.
And 3 people right there. Cool.
Perfect.
So yeah, if anybody wants to talk or make a game or whatever, come hit us up.
Surelink.com.
Yeah. Thanks.
Thanks, Pat.